In this video, we're going to talk about the zeros, or the roots, of polynomial functions. We'll try to understand, in some cases, how to actually find these zeros, and also try to cover some of the general theoretical results surrounding the zeros of polynomials. The basic setup is that we'd like to try to understand how to solve a polynomial equation, p of x equals 0. So here p of x is a polynomial, and the goal is to understand which values of x, when substituted into the polynomial, will make it equal 0. Recall that, by definition, any polynomial function takes the form shown here, right? So it's a bunch of powers of x, each one of which is allowed to be multiplied by some real number coefficient, and which are then added together. And it's customary to write the polynomial in a kind of descending order where the highest power of x comes first. The question, once again, is what values of x, when substituted into the polynomial, will make it equal 0. Accordingly, we say that a 0, or a root, of the polynomial p of x is a number, x equals a, with the property that p of a equals 0. So when we talk about zeros of polynomials or roots of polynomials, we're just referring to the values of x that make them equal to 0. That's the terminology. Let's begin by thinking about a situation that we already understand, namely the situation when our polynomial is quadratic or has degree 2. So written on the screen here is the general form of a quadratic polynomial, denoted q of x here. Q stands for quadratic. And we'd like to understand when it's equal to 0. In other words, we'd like to find the roots of this quadratic polynomial. In the most general terms, those roots are given by the quadratic formula, shown on the screen here. Moreover, we know that the roots of a quadratic polynomial happen to correspond to factors of the polynomial as well. So just to run through some particular examples, if our polynomial factored as x minus 1 times x minus 2, then we would know that it has 2 roots, or 2 zeros. If it factored as x minus 4 squared, on the other hand, then it would only have 1 root, or 1 zero. And if the quadratic polynomial had the form x squared plus 1, then it would be impossible to factor over the real numbers, and it would have no real roots. So a quadratic polynomial can have either 2, 1, or 0 real roots. And it's instructive to give some geometric interpretation to this idea as well. The graph of a quadratic function is a parabola, so shown here is an example of a parabola. Let's try to understand why there can be exactly 0, 1, or 2 roots, but not more, when working with a quadratic function. All we need to do is imagine the x-axis being drawn at different positions in this picture. So suppose, for example, that the x-axis were positioned like so. Well, then it would be true that our quadratic function has exactly 2 real roots, corresponding to the 2 points where the parabola crosses the x-axis. Another possibility is that the x-axis is positioned as shown here, just grazing the tip of the parabola. In this case, the quadratic polynomial would have exactly 1 real root, corresponding to the 1 point where it touches the x-axis. And finally, if the x-axis were positioned like this, then it wouldn't intersect the parabola at all, and we would find ourselves in the situation where the quadratic polynomial has no real roots. This geometric intuition is important for understanding why a polynomial of degree 2 can have at most 2 real roots. And the basic idea turns out to generalize to all polynomials. The most important result in mathematics regarding the zeros of polynomials is the aptly named fundamental theorem of algebra. Its proper setting is actually the system of complex numbers, not the system of real numbers. But one consequence of this theorem is that a polynomial of degree n can have at most n zeros. It can have at most n real roots. Moreover, it turns out, as we saw with our quadratic polynomial, that if x equals a is a 0, or root, of a polynomial p of x, then the polynomial p of x will have x minus a as a factor. It will be possible to write it as x minus a times some other polynomial q of x. And the degree of that other polynomial will be exactly 1 less than the degree of p. This also explains why if the degree of p is n, you can have at most n roots, because after you factor them all out, there can be nothing left except a polynomial of degree 0, which is just a constant. Let's see how the fundamental theorem of algebra plays out by considering some other polynomials. Shown here is the graph of a cubic polynomial, that is to say, a polynomial of degree 3. What we're going to do is once again try to imagine the x-axis being positioned at different places. If the x-axis, for instance, cuts through the graph of our function like so, then notice how we have 3 real roots, right? Because the polynomial crosses the x-axis 3 different times. It's also possible, however, for this polynomial, if it's shifted differently, to have only 2 real roots. So imagine that the x-axis cuts through the graph like this. And notice how this time there are only 2 points of intersection, and hence only 2 real roots. Another possibility, of course, is that the x-axis cuts through the graph like this, in which case there will be exactly 1 real root. But notice that there's something interesting happening with this polynomial, because no matter where we draw the x-axis, there must be at least 1 real root. There may be 2, and there may be as many as 3, but there must be at least 1 and at most 3 roots. This actually leads us to a general conceptual point, a general fact that's important to know, which is that if a polynomial has odd degree, then it is guaranteed to have at least 1 real root. And this is connected with the asymptotic behavior of polynomials of odd degree. They will always go to quote-unquote different infinities. The graph shown on the screen here is the graph of a degree 5 polynomial. And notice that no matter where we might choose to draw the x-axis, it must intersect the graph at least 1 place. All right, so polynomials of odd degree are guaranteed to have at least 1 real root. Let's do an example problem. This problem is asking us to find a formula for the quadratic polynomial whose graph is shown here. We can see that this quadratic function has a 0 at x equals 3 because it touches the x-axis there. And in fact, since it's only 1 root and this is a quadratic function, that 0 must in fact be a double root. So we can begin to write down our formula. It will be q of x equals x minus 3 squared. This at least will be a part of the formula. We're not finished, however, because the formula we've written down does not describe a quadratic function that passes through the point 0, -3, as required. The one bit of freedom we have remaining is to multiply the expression we've written down by a constant. Let me call it k. And the point will be to choose that constant in such a way that the parabola does have a y-intercept at y equals -3. When we substitute x equals 0 into our expression, set the result equal to -3, and solve for k, we see that k must equal -1/3. Therefore, the formula we're after will be the formula q of x equals -1/3 times x minus 3 squared. And it's fine to go ahead and leave our answer in that form. Now, how do we actually find roots or zeros of arbitrary polynomials? If we try to break the situation down by the degree of the polynomial, then there is a bit we can say. We know, for instance, that for a polynomial of degree 1, that is to say, for a linear function, finding the roots is very simple. It's given by the formula minus b over a, where a and b are the coefficients of the function. If the polynomial has degree 2, in other words, if it's a quadratic polynomial, then this time finding the roots is a bit more complicated, but it is given in a rather nice way by the quadratic formula. For an arbitrary polynomial of degree 3 or degree 4, there is also a formula for calculating the roots explicitly, but these formulas turn out to be very complicated, and basically no one bothers to memorize them. In the early 1800s, a young mathematician named Évariste Galois discovered something truly remarkable. He found that For a general polynomial of degree 5 or higher, there does not exist a general formula defined only in terms of radicals that will give the roots of that polynomial. And so, unfortunately, finding the roots of a general polynomial can be an extremely difficult task. One tool that can help with this regard is the so-called rational zero theorem for polynomials, which says that if a polynomial p of x, and here the leading coefficient and the constant term are given different colors in the formula, has integer coefficients, meaning that all those coefficients are just integers, then every rational number 0 of p has the form q over r, where q is a factor of the constant term a0, and where r is a factor of the leading coefficient a sub n. Again, any rational 0 of p will have that form. Recall that a rational number, by the way, is just a number that can be expressed as a ratio of two integers. We won't have time to go through the proof of the rational zero theorem here, but if you're wondering why it's true, it's not too difficult to understand. Try substituting a rational number into a general polynomial p of x, and see what must be true in order for that polynomial to equal 0. That will give you a sense for why this theorem works. Let's quickly put this theorem to work by considering an example. Let's try to find all possible rational zeros of the polynomial p of x given here. What the rational zeros theorem tells us to do is focus on the leading coefficient, which here is 2, and the constant term, which here is -4. And we'll begin just by considering the factors of those two numbers. The factors of -4, we're going to take the factors up to a minus sign, are plus or minus 1, plus or minus 2, and plus or minus 4. And the factors of 2, the leading coefficient, are plus or minus 1 and plus or minus 2. And so all we need to do is consider all possible numbers that can be arrived at by taking a ratio q over r, where q is a factor of -4 and where r is a factor of 2. And those numbers happen to be plus or minus 1/2, plus or minus 1, plus or minus 2, and plus or minus 4. Just consider all possible combinations. It's important to understand that these numbers are not by any means guaranteed to be the roots of the polynomial p. All the theorem says is that if p has any rational number roots, they must belong to the list that we've created. To determine whether these numbers actually are roots, you can of course simply substitute them into the polynomial and see if the result is 0.